All right, so in Bethlehem and Nazareth this year, I want to talk about the learning objectives through the end of Nazareth, what I would like to see the kids know going into Cana. So I'm going to talk about all the different things that I think they should know going into Cana at minimum. Some things that should be emphasized, some things that should be de-emphasized, and some tips on how to teach those different things. Okay, so first, addition and multiplication, certainly. I don't have subtraction and division up here. Why not? It's because, as I tell a lot of the students, subtraction and division don't exist. I say that sort of tongue-in-cheek. Of course, they do exist. But they exist as a sort of notational shorthand. And when we pull back that notational shorthand and see what these things are actually saying, it simplifies the teaching and removes confusion and ambiguity. All right? So 90% of those YouTube videos that say, oh, 50% of the people don't get this math problem right, they're using the ambiguity, especially of the division symbol. All right, so what do I mean? Addition is a very nice, very well-behaved operation. You have for any A and B, A plus B equals B plus A. You can shuffle the addition around all you want. Order of operations, forgot that. The reason I forgot it is because dropping subtraction and division makes order of operations much simpler. Also, A times B equals B times A. I would also encourage you to introduce the dot symbol for multiplication, right? It's easier to drop and is less confusing when we get to things like this in algebra, right? We drop even the dot when we have a number and a variable, right? Now, if we use the x, this would say 2x equals 2. That's confusing, all right? So I would much rather start using this dot as the multiplication than the x. That's traditionally used. Okay, now back to subtraction and division. Why is it a shorthand? Well, why is it bad? In general, unless A and B are the same number, A minus B does not necessarily equal B minus A. In fact, they're the negatives of each other. But if you peel back the notational convenience, the notational shorthand of subtraction, what this becomes is A plus negative B. So we don't need the subtraction. We can, every time we see something written as a subtraction, we can turn it into an addition of a negative. Okay? All right. And this is equal to negative B plus A, because addition is nicely behaved. All right, what about division? Division is the same way. Say A divided by B is not the same as B divided by A, unless, again, they're the same thing. But A times 1 over B is the same thing as 1 over B times A. We can shuffle these around now. All right? We don't have to worry about which comes first. All right? I'd say a large part of the difficulty learning subtraction and division is, well, if this one comes first and this one comes second, do I put the second one into the first or the first into the second? Right? This just bypasses all of it. All right? You've got a number times a fraction. Which is why it's so important to teach negatives and fractions. Okay. So let's dive into teaching negatives for a second. Negatives actually need to be taught a little bit differently when you're dealing with addition and when you're dealing with multiplication. Okay? So negatives with addition are a type of number, right? And they're a type of number that's the opposite of a positive. And when these things get together, they cancel each other out. I like to explain this with the Kilkenny Cats poem. There once were two cats from Kilkenny. Each cat thought 'twas one cat too many. So they scratched and they bit, and they fought and they fit, till except for their nails and the tips of their tails, instead of two cats, there weren't any. And that's what happens when negative numbers and positive numbers get together. They sort of destroy each other, and whichever one has more is what's left. Right? So if you have, 3 positives and 5 negatives, right? Well, you have 2 more of these negatives than you have of these positives. So you have 2 of the negatives left. Right? Okay. Multiplication is a little bit different. Multiplication, you really need to lean into the idea of negative as opposite. Okay? And the opposite of a positive is a negative. But importantly, the opposite of a negative is a positive. All right? So, suppose we have something like -3 times -3. All right? So, what I would like the students to read this as, to parse this as, is the opposite of 3 of these -3's. The opposite of 3 of these -3's. What is 3 of these -3's? Well, it's a -3 and another -3 and another -3. All those together is -9. So the opposite of 3 of these -3's is the opposite of -9. The opposite of a negative is a positive. There. Now, if you do something like this, well, it's just 3 of these -3's. -3 and another -3, that's more negative, and another -3, that's more negative, -9. Or you could read something like this. This is the opposite of 3 times 3. Well, they know 3 times 3, that's 9. The opposite of 9 is -9. Right? Okay, so that's multiplication. Now comes the hard part, explaining fractions. So the way I would introduce it is maybe something like this. Is this a number? Yes. Well, yes, but actually no. This is a picture. It's a squiggly line. Right? It's not a number. A number is an abstract concept. It's like the concept of this muchness. Right? It's like this is the territory. The abstract concept of this muchness is the territory. This is the map. All right? They're different things. Why is that important? We know how to manipulate these. We know that when you have this muchness and you put this muchness more of it, you get ba ba and ba ba ba, and you get da 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 da. There. That's fun. Or this many sets of this much. All right? So you have this much, this many times. That much. Now, so we can figure out what is the answer to 2 plus a mystery number is 5. We can do that. Once we've learned negative numbers, we can get the answer to 5 plus a mystery number is 2. All right? But what about this? What about 3 times a mystery number is 2? 3 of these things, whatever they are, is 2. Run through all the whole numbers you want, you'll never find a whole number like this. And so, if all we had is whole numbers, this would have no solution. But mathematicians hate having no solutions. And every time, almost every time, that they come across a problem with no solution, they make up a new type of number to give it a solution. It's incredible. So, what is this saying? It says 3 of these is 2. Okay, we can sort of imagine a number that 3 of them is going to be 2. We know it's going to be less than 1 because 3 ones are 3. Well, we know it's going to be greater than 0 because 3 zeros are 0. So it's somewhere in between 0 and 1. Right? And so we give it a name. We give it a representation. We give it a symbol. We put it on the map. The territory is a number that 3 of them makes 2. But our map, our symbol, is like this. 3x is 3 of these makes 2. Right? So, let me ask you, if 3 of these makes 2, what does 6 of these make? 4. So, we could have a different looking representation that actually means this same number. Right? It's the same point, same place in the territory, but it looks differently on the map. It's a weird map. We can say 6 of these things make 4. All right? Okay. Another way to think about these fractions is suppose you have bread that is 3 big. All right? And you're going to spread 2 butter on top of this bread. Right? Well, you can't do it evenly in whole units. Right? You'll have bread left. So what you need to do is chop a little bit off of here and a little bit off of here. And then you have there. It's nice and even. And the number 2 spread over 3 is the thickness of the butter. That's another way to look at it. Okay, that is all the way up to fractions. Negative fractions, if you remember, we need to talk about addition of fractions and multiplication of fractions. Whew, gee golly. All right, multiplication of fractions. Okay, so let's think. Let's do a simple one. Half of a third. Half of a third. Well, if we take if we take a third, right? 1/3. And we cut that in half. Well, when we cut everything to the same size, these become sixths. And so this is, so half of this, 1/2 of it, is 1/6. I never did like that explanation much, but it's hard to come up with a better one that actually carries the concept. But I'll try. All right. So here we have 2 of these things equals 1. And we want this many of these. So 2 of these becomes 1. So we want 2 of our answer to become 1 of these. 2 of our answer becomes 1 of these. So we could write it like this. 2 of our answer becomes 1 of these. Well, okay. Now, let's think about this. What would 4 of our answer become? The same number. Well, 4 of these, if 2 of these is 1 of these, 4 of these is 2 of these. There we go. What about 6 of them? If 2 of these are 1 of these, then 6 of these are 3 of these. But what does this mean? This number here says 3 of this number is 1. And we have 3 of this number. So this is 1. Okay. Let's do the third way. Well, let's do another example of this. Let's do 4/3 times, say, 2/5. Okay? All right. We want 3 of these. No, we want 3 of these. 3 of these to be 4 of these. 3 of these equals 4 of these. So 3 of these, no, 3 of these, yes, 4/3, is, no, no. How does that work? Okay, simpler way. Three of these is 4 ones. 3 of these is the number 4. Okay, so that's the same, well, and then I'll write down the 2/5. But 3 of these is the number 4. So, that's the same as having 4 of the number that 3 of these is 1. And this, since 5 of these is 2, that's the same as twice the number that 5 of them gets you 1. I might have to practice this a little while to make it a little bit more intuitive. But this is the number, 3 of which gets you 4. So it's the same as 4 times the number, 3 of which gets you 1. This is the number, 5 of which gets you 2. So that's the same as twice the number, 5 of which gets you 1. Now, since multiplication can be shuffled all around, this is 8 times a third of a fifth. Now, this here is the same as 3 gets you 1/5. 3 gets you 1 of these 1/5. So 8 times 3 gets you 1 of these 1/5. All right? Well, if 3 gets you 1 of these 1/5, what does 15 of them get you? 1. So this is 8/15. Another way is, let's see. Well, another way is the purely algorithmic way. All right? Whatever number you have over whatever number you have times whatever number you have over whatever number you have, it's A times C over B times D. All right? That's perfectly true, but it doesn't really teach anything. Okay. Doesn't really explain. It's true, but it's not an explanation. Now for the really, really tough part, addition of fractions. Okay. So, 2 gets you 1 of these. 2 of these gets you 1. 3 of these gets you 1. But we can't really put them together because do we take 2 of the result or 3 of the result? Do we know what we get? Does 2 of this addition get 2? No, because 3 of these gets 1. Does 3 of these addition get 2? No, because only 2 of these gets 1. All right? So, again, you have to ask yourself, if 2 of these gets you 1, what does 6 of these give you? 3. 6 of these things get you 3. So this is just as valid a symbol for this number as this. Because 2 gets you 1 is exactly the same as 6 gets you 3. That's the same concept. So these are the same numbers. This, if 3 gets you 1, what does 6 get you? 6 gets you 2. Now, if 6 of these gets you 3, and 6 of these gets you 2, what happens if you have 6 of both? You get 5. 6 of these gets you 5. Cool? You might explain it like buying fireworks. You know, you have fireworks deals, buy 1, get 2 free, right? I guess that would be opposite, wouldn't it? That would be 1 gets you 3, not 3 gets you 1. Never mind. Another way, same thing. If the student has mastered multiplication of fractions, even if it's just the algorithmic approach, you multiply the tops, you multiply the bottoms, right? Then the approach is, let's say, 3/7 plus, let's not use sevenths, let's use eighths. and twelfths. And 5/12. There we go. 3/8 and 5/12. Well, what you can say is we can't add these directly because they're not the same type of thing. Right? These are eighths. These are twelfths. That's why we use the ths. Right? We're saying what type of thing it is. Or if eight of these whole things gets you 3, 12 of these things gets you 5. Right? They're not the same type of deal. But we can turn them into the same type of deal. Here's where factoring comes important. Because 8 is 2 times 2 times 2. 2, 4, 8. 12 is 2 times 2 times 3. Well, so these are common. 2 times 2 times 2 times 3. Right? 24. All we got to do is multiply by 1 in a sneaky way. Right? Well, another name for 1 is 3 of these 1s gets you 3 of these 1s get you 3. That's another name for 1. And here, 2. Right? 2 gets you 2 is a sneaky way of saying 1. All right, so here, and if you know how to multiply fractions, that's 9. That is 24. That's 10. That's 24. And since we have the same type of things, if 24 of these gives you 9 and 24 of these gives you 2, then 24 of the result gives you 19. Right? Okay. So that's fraction addition and multiplication and addition. I would strongly advise to teach fraction multiplication first. Fraction multiplication first. Because fraction addition is built on fraction multiplication. Okay, what about fraction division? I showed you sort of how to divide whole numbers by turning one of them into a fraction. What about like 3/5 divided by 2/3? Right? Well, I'm sort of at a loss for how to describe the concept behind this. The algorithm is easy. Mechanically, how to do it's easy. Take the reciprocal of this number. That's mechanically how it's done. But conceptually, it's how many of these are in that. But why is that the same as this many of these? To try to connect those two, I think I could do an analogy with whole numbers. So like 6 divided by 2, right, is how many 2's are in 6. Well, that's obviously 2, 4, 6, 3. But that's the same as saying two of whatever our answer is gets you one of these 6's, which is saying 6 can be divided up into 2 groups of how many, which is another way of interpreting this. And of course that's 3. But trying to explain why this works, this reciprocal works, it's the same reason, but chasing around the different numbers and the different sizes. That would probably be pretty difficult. So maybe this you just have to do mechanically, algorithmically. Maybe using something like this for an example. Okay. So, and of course subtraction is just make one of them negative and then make sure they're the same thing, kill kitty cats method. Okay. Let's skip to order of operations. If if one teaches just multiplication and addition, there is no need then that's an A, for this inaccurate mnemonic PEMDAS. This is actually inaccurate because multiplication and division have the same precedence because they're the same operation. Addition and subtraction have the same precedence. It's the same operation. So instead of teaching these 6 things and group these two, multiplication comes before addition. That's all you've got to know now. Multiplication comes before division, exceptional cases, parentheses point out exceptions. Parentheses point out exceptions. Parentheses make anything inside the parentheses into a single number. All right? So that's it. That's order of operations. Multiplication comes first. Parentheses adjust that. Parentheses point out exceptions. That's it. All right, factoring. Factoring. Why is factoring very important? Factoring is very important. We've been implicitly doing factoring and multiples every time we've been using fractions. So if you want to do 120, say 120 divided by 36, something like that. 120 divided by 36. Well, how in the world are you going to do that? Well, you can factor out a 2. You can break this 120 into 20 times 6. And you can break this 36 into 6 times 6. All right? And then, well, you can do the multiplication of fractions backwards. Backwards. Like A times B over C times D is A over C. Oh, what am I doing? A over C times B over D. Well, 6 gives you 6 is the same as 1. Times 1. Here again, we can break it down. This is 10 times 2 over 3 times 2. Do the same thing, 10 thirds. Okay? So the ability to factor, to break numbers up into factors, is a very important skill for among other things, for simplifying fractions. And so you might want to throw in here prime versus composite. A prime number is a number that cannot be broken up any further. 7, all you can do to write that as a multiplication is 7 times 1. Right? Or you can resort to fractions. Right? But if you're staying within the integers, 7 can't be broken down any further. Then again, 9, and I always get this conjecture from the little ones that every odd number is prime when I start to introduce the prime numbers. Because it's 3, 5, 7, well, 2 is prime as well. 2, 3, 5, 7, and they think they notice a pattern. It's like, it's all the odds. Nope, 9 is 3 times 3. And then it gets interesting. Because a prime number has to be odd, because it can't be even, but not all odd numbers are primes. Now it becomes interesting. All right. Okay. And knowing how to tell if a number is prime. So, if you get into this prime versus composite, you can get into divisibility rules, which are cool. Like if a number ends in 2, 4, 6, 8, or 0, it's divisible by 2. Or if the digits of a number add up to a multiple of 3, the number is a multiple of 3. If the number ends in a 5 or a 0, it's divisible by 5. If the digits of a number add up to a multiple of 9, the number is a multiple of 9. There are also rules for divisibility by 7. Divisibility by 10 is easy if the number ends with a 0. But divisibility by 11, there's rules for that. They're complicated, though. They are very complicated. Okay. Factoring, order of operations. The only thing I haven't talked about is whole integer exponents. Distribution. Haven't talked about distribution. So distribution is what I call the bread and butter of arithmetic because it is so ubiquitous in mathematics. Algebra, it's used all over, both backwards and forwards. All right? And the concept is this. All right. This diagram will probably throw your students for a loop, right, for a bit. Because this dot, dot, dot. And you say there are A boxes. Like, what is A? A could be anything. Is A 3? It looks like 3. No, not necessarily. There's this dot, dot, there's some boxes in here. Oh, so it's more than 3. Not necessarily. It could be 1 or 2. But why did you... It'll throw them for a loop. It will. I've heard all of it. To try to like abstract the concept that there's some number of boxes here. And let's call that number A. That's a hard one to get across. So you may want to actually make, like, there's 3 boxes. Right? You may want to start with a concrete example. But in this box, there are B bananas in each box and C carrots in each box. Okay? All right. All together, how many bananas are in the box? Boxes. How many bananas are in all the boxes together? Usually takes a while to pull this out, but it's A times B. So A times B, that's the total number of bananas in all the boxes. What about the number of carrots in all the boxes? Well, that's A times C. All right. Now, if we want to answer the question, how many pieces of food are in all the boxes combined, we just add these two. There's this many bananas and this many carrots. So far, so frosty? All right. Now, another way we could ask the same question is how many pieces of food are in one box? Well, there's B bananas and C carrots. So in a single box, there is B plus C pieces of food. Now, to get the total pieces of food in all the boxes, we can multiply by the number of boxes. So A times B plus C is the same thing as A of B and A of C. All right? Very, very important. And this is used both ways. This is used for factoring something common out of an expression and for distributing a factor into a number expressed as a sum. Okay, I just realized that I'm using a lot of jargon that I haven't defined. So maybe a quick rundown on some of this jargon. All right. So let's say A, B plus C minus D plus negative D times E plus F times 1 over G, or Q, right? So this whole thing is an expression. It is not an equation. An equation involves an equal sign. So if I said, that's an equation. This is an expression. Now, notice this expression has one or more pieces that are added together. These pieces that are added together are called terms. Right? Each term is made up of things that are multiplied together. So here and here, these two things that are multiplied together are called factors. And notice that one of these factors is made up of two terms. So they can be nested. This definition can be nested. So an expression is a bunch of terms added together. Each term is a bunch of factors added together. Factors can be sums of terms and so on and so forth. Okay. But this can always be, by the distribution rule, rewritten as just a sum of terms. And the terms all being just products of factors. So this could be A times B plus A times C, and it's all just sums of terms, which are the terms or products of factors. Okay. Any more jargon? Reciprocal. The reciprocal of A divided by B is B divided by A. All right. Other types of jargon usually introduced in grade school. Most of it I don't like add-ins and add-ins. No, I don't like that. They're terms. The something and the subtrahend. No, nope. Subtraction doesn't exist anyway. Numerator and denominator, I'm kind of fine with. Let's see, what else? Quotient, I'm actually fine with. Remainder, I'm very fine with. I actually like quotient and remainder. Oh, that brings me to another pet peeve of mine with fractions. Okay, pet peeve of mine with fractions. Mixed numbers need to die. Here's why. So, like I said at the very beginning, I prefer multiplication to be done with a dot. So that later on, when we start using x as our primary variable, we can just say 2 times x or 2x. And in this case, juxtaposition of two things that are different kinds, a number and a variable, juxtaposition, which means just putting together, implies multiplication in this context. But now look at a mixed number. I hate even writing that. Because to me, that's juxtaposition of two things of different kinds, and this should be equal to 1. How a number with a whole part and a fractional part, if you want to highlight the whole part, here's how you should write it. So, that's more true. That's true. 3 and a third. Not this, please. If you see this in a workbook, you don't have to say it's wrong. Just make the point. Just make the point that this means that. Okay? And maybe you could put a little plus in there to make it clear for you. Right? Okay. All right. What else? What else? Whole integer exponents. We haven't even done that. All right. Whole integer exponents are actually not too bad. So what a to the b means is a times a times a b times. It's a repeated multiplication. So 5 to the third equals 5 times 5 times 5, which equals 125. All right, just repeated multiplication. And that's about it. That if a student comes into Cana knowing how to do all of that, I'd say that's a success and a half right there. I'd say that's a success. They are going to be successful in pre-algebra. They're going to be successful in algebra. Okay? So that is the learning goal for the end of Bethlehem. Now, up to you, how much of this You teach in Nazareth, you know how far you go in Nazareth, how far you go in Bethlehem. No, sorry, I meant the end of Nazareth. It's up to you how far you want to go in Bethlehem, how far you want to go in Nazareth, where you want to break that up. All right. I would suggest that it overlap quite a bit, because review is never wasted. Preview is never wasted. All right. So some of the younger kids can see some of the advanced stuff, right? And it plants the seed for later. Some of the more advanced kids can see the more basic stuff, and it refreshes that circuit. All right? So never be afraid to preview or to review. All right? So widen the scope. Widen the scope of your lectures. I'll talk about games in another video. Thank you. Here's the off button.